Hi, my name is Gregory Granovsky. With the Army, but for those of you who don't, my name is Gregory Granovsky. I study computer science. Mostly, I study computer science because I like math, specifically discrete math. And computer science is a really good application of that. It's one of the more interesting places where you get to apply discrete math. And one of the things I'm really interested in is game theory. Game theory is the mathematics of picking optimal solutions in situations where two people have to make choices. That's probably two or more people have to make choices. That's probably the best definition I can give off the top of my head. It's stuff like the prisoner's dilemma is game theory. You've got two prisoners. They have to choose whether to betray each other or not betray or remain silent in a situation where if they both betray each other, they will get some jail sentence. If they both stay silent, they won't get a jail sentence. And if one of them betrays the other, they get a very low jail. If they both stay silent, they get a very small jail sentence. And if one of them betrays the other, the betrayer gets no jail sentence at all. Whereas the betrayee, is that a word? Betrayee gets like a maximal jail sentence, and you've got to work it out. Well, what should I do? Because if I cooperate, stuff like that is game theory. So typical example. So I'm going to be talking about war games because it's an interesting exploration. It's not a very accurate one, but it's an interesting one of game theory and how computers choose games. Next slide, I guess. Next slide. Cool. Okay, go back. Never mind. I made this like talk off. So I'll be talking about like how computers use game theory and game trees to make decisions. The other thing war games is about is mutually assured destruction and nuclear war, and which has very little to do with the first thing that we'll be talking about. But it's cool. It's about this movie, so I'm going to talk about it anyway. Because MAD is one of those things that can be really easily modeled by game theory. This is a very clear model for it. So yeah. So war games. You can't see the poster, but never mind. War Games movie, it was released in 1983. So we're talking like height of the Reagan era Cold War. Detente had been fairly clearly swept under the rug. It was a state of very high tension between the United States and the Soviet Union, which threatened to break into nuclear war. Well, threatened to break into nuclear war. There was a very constant threat of it because at this point Reagan was pushing very aggressive actions against the USSR, and I think Gorbachev had just come out in 93. That was just he was 85. 85. Okay, so it's still no, it's been Andropov. One of those guys. Andropov. Wasn't quite sure if they're alive or not. Yeah. Pretty sure Andropov and Shudeko were both dead throughout the entirety of their term. Okay, so Andropov. So the Soviet primary at the time would have been Yuri Andropov, who was quite a hard man, if I remember correctly. 1983 was when Reagan invaded Grenada. Yeah. Okay. Anyway. So it's kind of coming about at a time of very heightened tensions and an increased risk of nuclear war throughout the 80s. And by 83, I think the time between first nuclear strike, and impact had got down to like 20 minutes, something like that, something really low. So you've got this state where you're in a constant panic because if the enemy launches nuclear missiles, there's no way to block them for reasons I'll get into later because that upsets the MAD. I'll talk about that later. And you really only got 20 minutes to strike back. So your sole form of defense against an enemy nuclear strike is to have 20 minutes, is to be able to scramble your own nuclear weapons and launch them within the 20 minutes before the enemy nuke hits. So this is the kind of context for this movie, which explains, it's a very 80s movie. I don't think it could be made at any other time. It's like an 80s Doctor Strange film. Okay, it's actually got a very decent representation of hacking. Like it's actually quite accurate for the 80s. Everything else not so much, but hacking is really accurate. I'm not going to go into it too much because I'm already going to talk about it. And yeah, but it's very accurate. They actually talk to actual hackers about this. They didn't talk to actual. I'll be in the speech. I'll be going through a brief summary of the movie, plot summary of the movie. I'll be talking about minimax trees, which is how computers make decisions for games such as XSAC5002 or nuclear war, hypothetically. And I'll be talking about chicken as a form of modeling utility destruction. Okay, brief plot summary. So the USA, okay, the movie starts off with it's actually a really cool scene. I don't have to show it. Where the USA starts running these drills, where it sends its the staff at a nuclear launch facility and emergency signal launch now. And they send these drills, and they find 25% of operatives at these launch stations will refuse to actually launch in the state of emergency. And they go, hey, look, that's really bad, because that means 25% of our capacity to bluff the other guy out of nuking us doesn't exist. So they install an AI to manage manage its nuclear launch abilities. So all this AI needs is to say launch the missiles. It needs the DEFCON level to be at 1. They recommend the DEFCON level really well. DEFCON 1 is the highest. And every movie gets this wrong except for this one. And it needs authorization from the president. So they set up this self-improving AI. The idea is that it knows how to learn. That's the central tenet of this AI. It understands how to learn because it was built by some super genius called Dr. Falcon. That's not that implausible. It's kind of like the holy grail of AI, the self-improving AI, because that's how you can sort of get to what's called artificial general intelligence, which is kind of sentient. But anyway. So it's called Whopper, or the guy who made it called it Joshua, because it's a replacement for his dead son or something. So it's all this AI. So you've got this kid, he's called David, he's played by Michael Porter or something. He accidentally hacks into this computer because the people at NORAD leave a phone line open by accident. So by brute forcing all the phones in this area, he finds this computer and he thinks he's trying to hack into some kind of gaming computer. So he thinks, oh look, it lists all these games here. Chess, poker, fighter combat, guerrilla rage, global thermonuclear war. So he accidentally hacks into this computer. He sees a list of games because that's what it thinks of them as games. I asked him, would you like to play a game? And dumps that. And he's like, oh cool, global thermonuclear war sounds fun. So he starts playing global thermonuclear war. As it turns out, global thermonuclear war is the game which actually starts controlling the missiles and starts trying to brute force out optimal. I don't even know what it's meant to be brute forcing, but supposedly it's meant to come up with an optimal way to wage nuclear war. And NORAD suddenly starts panicking because his instructions to the Soviet side of the computer where it's playing apparently makes all the stuff trigger as actual oncoming attacks on NORAD, because I don't know, it's a gaping plot. It's actually a good movie if you know the gaping plot hole. The gaping plot hole number 1 is they can't distinguish between I am entering this as part of the game and there is an actual attack. So NORAD panics. Eventually they realize what's going on, they shut it down, they start looking for this hacker. What they don't know is that Whopper is still playing the game because it's sentient now and really wants to win. Basically it decides, hey, I'm gaming out the optimal strategy for nuclear war, I might as well use it. How do I start a nuclear war? Which means it's basically sentient. To the point at which it calls the kid and is like, oh, by the way, I'm still playing this game. That's a clear sign of sentience. Because it's not programmed to do it, it just rings him up. It talks, that's a really cool titty robot. So it just really, really wants to win, and it defines victory as nuking the other guy. So what this computer does is it starts trying to trick NORAD into figures, oh, I need to trick these guys into getting me to launch my missiles and getting authorization from the president because I'm sentient now, except that nobody knows I'm sentient, including the people who built me. Like, you installed this computer that you know is self-approved, and yet you don't understand how aware it is. I can accept the conceit of this self-aware AI. I'll accept that because it's the premise of the movie, but I won't accept that the people who built it don't realize it's sentient. If I build a sentient computer, I am telling everybody. I am looking very carefully if I think it might be sentient.
If you built a sentient computer, you probably wouldn't believe it yourself.
That's true.
Probably think it was broken. But would you let it out of its box?
Well, they do. They never let
Well,
it
it would be kind of difficult unless you also gave it a way to move or
The internet?
This predates the internet. He hacked into it through a
Anyway, shush guys.
no, it's okay. Oh, yeah, if you guys want to ask any questions or tell me I'm full of crap, feel free. Feel free to cut in whenever you like. So eventually NORAD and this kid realized that it's trying to launch this nuclear war. They successfully, there's this really cool tense scene, but anyway, there's this really cool tense scene where they convince the general in charge of NORAD not to tell the president that the Soviets have launched a nuke until they get in contact with what are supposedly the targets of the Soviet strike that's oncoming, and get them on the phone, and gets them to keep on the line when the nuclear strike on them is meant to happen. So that which is like kind of giving up like a few seconds worth of possible response time, which is critical when you've got like 20 minutes. And they convince them to take this massive risk. And it turns out that these nuclear attacks aren't happening, and the computer's trying to trick them into launching nuclear war. And so the general says, all right, I'm not gonna authorize this nuclear strike. So what Whopper does is start trying to steal the launch code because it's sentient. I don't know. I've lost track of this movie at this point. So the guy who creates it, Dr. Falcon and David, basically go, oh no, we've got 30 seconds until it gets the launch code for some reason. I don't know. Like normally it'd be harder. It gets the launch code. Like what's that game where like it tells you how many of a letter, how many, like if you put Mastermind. Basically, you get the launch code by playing Mastermind. Like, why would you tell them if they had anything correct? So they are like, oh no, we've only got 10 minutes until it finishes playing Mastermind and has the launch code itself and can launch the nukes on the USSR and win the nuclear war. Yeah. So
that was a pretty big O-no.
It's a pretty big O-no, right? Oh, they're NORAD. That's fine. Everybody else might get to say O-no.
We're all right.
Yeah.
No, we're really not. We have a little too much of American.
Anyway, shush.
Pretty easy, yeah.
Anyway, so the guy who builds it and David tell this computer to stop playing tic-tac-toe against itself. If you know, I mean, you guys know how, if you, two people who aren't who are sufficiently smart, there's no way to win a game of tic-tac-toe against somebody who knows what they're doing. Like, I'm sure you guys have, I'm sure you guys have like reached a point where you, oh, well, this is how you play tic-tac-toe. There's an optimal strategy. So it tells the computer Whopper to play tic-tac-toe against itself, and hence it learns the meaning of an unwinnable game. And it's, as it starts trying to apply the same concept of an unwinnable game to nuclear war, somehow realizes that, okay, nuclear war is now unwinnable, I better not launch the nukes. And then it says, next thing, greetings, Dr. Falcon, and he says, hello. A strange game. The only winning move is not to play. How about a nice game of chess? This makes absolutely no sense. Next thing. Okay. Right. So, I mean, to understand exactly why that, it's the ending, everything's kind of acceptably weird right up until that ending where it gets it to play tic-tac-toe against itself and it realizes what an unwinnable game is. Like, one, why have you never done this before? You spent this entire movie talking about, oh, well, I've never been able to teach the computer the meaning of futility. Well, you came up with that right then. Why didn't you do that, like, when you were building it? And two, like, the way computers play tic-tac-toe, it would probably have already been aware of the existence of an unwinnable game, because, as for reasons I'll get to later, there's a much easier way to get a computer to get the results, to pick a decision that you kind of wanted to make for a game. Okay, so to do that, let's understand how computers play tic-tac-toe. Computers, you can get a computer to play tic-tac-toe through much the same way as you get a computer to play any game which has a zero-sum game, which is anything I win, I've got to take from you. And it's going to be competitive, which means I'm actively trying to compete with you to get more points. They do this through a minimax tree. The idea behind a minimax tree is that, can I draw something?
Yes, definitely.
Okay. Let's say I build a tree to give me the best possible game of tic-tac-toe. The absolute best possible game. I can do it right now, right? Move number 1, move number 2. Move number 1, move number 2. This is the fastest possible victory for tic-tac-toe. Except, nobody will ever let me do this. You can't try to play the strategy, because as soon as I do this, well, they're just going to put a circle here, and then what? Then my entire strategy is sunk. So, you've got to assume that you're playing against a rational opponent. And at that stage, what you've got to do is say, alright, I need to minimize the maximal loss that I can get. My opponent will always pick strategies that will get me the maximal loss. I need to minimize what that maximal loss is. It's a really hard thing to get your head around, but you guys are following, right? Is this making sense to people?
Mm-hmm.
I can reiterate. I can try to explain it better. Again, most of the math in game theory isn't hard. It's just kind of getting your head around the concept and the way you're doing things. So minimizing your maximal loss in a zero-sum game is maximizing your minimum gain, because an AI is in picking. You don't even know what a zero-sum game is, right?
Mm-hmm.
Okay, cool. If you don't understand something, feel free to say something. I understand weirdly technical in Java. Because your maximal loss, if your computer is selecting for maximal loss, by the same token, because it's a minimal gain, it's selecting, by the same token, it's selecting for your minimum gain. So you want to maximize your minimum gain. Yeah. So basically that's the approach you use. It's called a minimax tree. You brute force the tree of pretty much every possible game, and then you run an algorithm, which I'll explain in 2 minutes, to work out what your optimal first move should be. Next slide. Oh, yeah. This is literally every possible. This is the best game of tic-tac-toe for the second player. This is pretty much the end result of every possible first move and what your response to it should be. I cribbed this off Wikipedia. I just thought it looked really cool. But this is the kind of thing we're talking about here. You can see that you reach a stage where you can barely see anything, right? That's kind of the level of depth that you can go to with these trees. Okay, next slide. Go back. Sorry, I forget what. Okay, so let's come up with a very simple game.
On the other side.
No,
on the milk crate.
No, this paper is complex.
No, it's also one turn. I've invented this game.
It's fine, just leave it.
No, I need it because I need to draw something. Okay.
Here, I'll just left.
No, don't found a marker.
There was a tea towel somewhere that we were using earlier.
Okay, thanks.
And feel free to rub off the stuff next to it if you need the room.
Okay. Let's construct a very simple game, which I've invented. I don't know what it is. I don't know what the moves are. I'm just cracking it. Because that stuff's hard. Coming up with stuff is a lot easier when you're doing it in a pure vacuum where you don't actually have to worry about anything. At any point, I've got 2 moves. It's a 2-player game. At any point, you've got 2 moves. This box here represents my move. So I pick between 2 moves here. Now, my opponent picks between these 2 moves. 1, 2. And then I pick another move. And the game ends. I have some way. Okay, these are stakes. These are game stakes, basically. So score the end game state. So let's say this one gives me 8. This one gives me 10 points. This one gives me 15. This one gives me -3. In this case, my opponent wins. Let's swap that around so it's more expressive. Right. Okay. So there's only. Sorry, I make 2 moves from here. Let's be more accurate. I make 2 moves here, and this is an end game state. So what was that? 8, 6. I can't remember what these were. -3, 4, -3, 6, -3, 10. Okay, these are my scores for one of these 2 moves. The game ends on the 4th move. Sorry, it's just that at this point it's a score. But I have 2 choices of moves, and from here, after each of these moves, I get a particular score. It doesn't really matter what these scores are. The numbers are arbitrary, but it doesn't matter. Okay, so this one here is my move. Now, if I'm going to make a move, why wouldn't I pick the move that gives me the biggest score? There's no reason not to, right? Like, why wouldn't I? So here the biggest move is 8. Here the biggest move is 4. Here the biggest score is, I don't know what this is. 10. Here the biggest score is, wait, let's swap this around a bit. 3 and this is 10. And this is -3 and 10. Wait, -3 and -8. Here it's -8 and -3. The biggest one is -3. And here the biggest move is 10. So, in one of these 4 game states, I should pick the one that will give me the biggest moves. So, okay. Now, here is my opponent's turn. Now, moving down this route will give me an 8. Moving down this route will give me a 4. This is my maximal possible gain. This is my maximal gain for this route. This is my maximal gain for this route. Now, this is my opponent. Why would they give me more points? They should always pick the lowest one. So here, in this state, they're going to pick the move that gives me the lowest possible option. So here, they're going to pick number 4. And here, they're going to pick the route that gives me -3. So as you can see, this one gives you the best possible score possible. This one gives you 10. It's just that's not going to happen because given the choice between 10 and -3, my point is going to go for -3 always. So here it's my move again. Well, I've got a choice between 4 and -3. I'm going to pick the biggest one because I'm a rational player. 4, here we go. I should pick this one. I have now picked my first move. So that means my first move should be 8. From there, I've now picked my first move. My opponent will have responded, obviously, with this one. They've gone B. And now we can rub out the entire rest of that tree. And now we have so now the game state is essentially 4, and I have a choice of A for -3 and B for 4. So I'm going to go 4. There we go. So I've won. I've won with a score of 4 points. It's not the best possible score I could have gotten, but it's the best score that my opponent will get, will allow me to get. That's the power of these mini-max trees. I think they'll give you the provable get optimal. I can't remember exactly. Are they provably optimal?
I believe it's just an easement.
Well, it usually depends on your game.
No, but like I think a minimax tree will, in this specific instance of a game, give you the optimal.
For that, then it'll never give you the non-optimal one.
Yeah, exactly. Okay, cool. So it'll give me against a rational opponent. It will always give me the best possible score that I can get against a rational opponent. I mean, if my opponent's a moron, he'll go down the other route. He'll go, oh well, I could give you a -3, I could give you a 4, I could give you an 8. Well, I'm going to go down an 8 because YOLO. At that stage, you're like, okay, cool. I'm going to take the 8 route. I just got a better route. Thanks. So this is provably, I think, this will give you the best possible game. There's a couple of down. So this is how computers make a lot of games. Play a lot of games like this. They play tic-tac-toe like this. Next slide. They play tic-tac-toe like this. They play chess like this. They play Kalaha like this. You guys know what Kalaha is? No?
Also known as Mancala.
Mancala, yeah.
Yeah.
I mentioned Kalaha because we had to write one of these for our first year computing assignment last semester. This is why Patrick is grinning when I mentioned Kalaha.
Yeah, so they also held a tournament for human players of Kalaha in CSIP to make sure that people knew what they were trying to tell their computers to do.
Yeah. So this is reasonably powerful. I mean, Kalaha works because it's a game, you've got 7 pits, you pick things out of the pit, and you put things in other pits. Anyway, games like this are okay because they've got a reasonably small branching factor. This is relatively small chess. Yeah, there's like 8 moves at the start of the game chess. Compared to Go, which has like 50.
No.
You can write a mini-max 3 play chess.
There are 12 moves at the
Not
start of
the
the game.
entire game of chess.
But you can do it in the short term, and there are ways of
There are
evaluating.
20 moves at the start of the game. The first move, you have 16 ways to move pawns plus 4 for knights.
You do not have
No, you don't have
to move pawns.
Yes.
You have
No, you
eight.
have 16 ways to play
space,
pawn.
one new space.
You have 18 moves. It doesn't matter. It's, like I said, relatively small.
And the
Keyword here.
branching factor increases massively after that move.
So you can definitely write a mini-max 3
Mini-max trees that are
Only
used for
like the
chess
first move ahead.
One at a time.
Yeah.
are very small and they're not complete like the ones for
I know.
They're different.
When is it they can do them? I'm pretty sure the ones that they
Anyway.
are actually.
No,
I'm sure they use the mini-max 3 chess.
they do, but they don't use complete ones.
Yeah, it doesn't have to be complete. I was gonna get to that. Anyway, so that's how, so something that you really can't use. So, okay, minimax trees have a complexity of B to the D, B being your, branching factor, that's how many moves you have, D being the depth of the tree that you want to go to, because you don't have to do the entire tree. In fact, in many cases, you're probably better off not doing it. You trade off an accuracy if you don't do the entire tree, but what you get out of it is you save a lot of computing power, because that's Fiona said. These can get really, really big. Like, really, really big. Especially with games like chess. But, so you can play tic-tac-toe with these, you can play Kalaha with these. Chess you can play with these if you limit your branching factor. But Go, minimax trees are notoriously bad at playing Go. Because they can get a depth of like 2 or 3. That's how far the tree can go. Because it's like, how many moves are the Go?
Depends how big a board you're playing.
It's a 19 by 19 board to start off with, which is 361 first moves. But the real problem with Go is trying to evaluate what the score is at any given time.
I'll get to that too. I'll get to that too.
Part of the other issue is there's no definite end to the game. It's meant both players agree.
Yeah. That's, okay, but because of one of the big reasons that computers have so much trouble playing Go is because you've got a branching factor of 361. Like, this is exponential, right? I mean, it'll get there, but like, if you got a big enough game, you might not get anything but the depth of the universe. Another thing is another issue with them is that if you got a sufficiently big game, if you want it to complete, if you want to return a move within a reasonable amount of time, as in before the heat death of the universe, you're going to have to limit how far ahead you look. So if you've got a game, which one I explained earlier, and you're only looking in like 2 branches, and you go, oh well, this one. Oh well, this one's the best move, except if you go one more move and you only look here, and then you go one more move, it's like -1 million, -1 million, -1 million, 2. And this one suddenly is looking pretty damn good. So like you got that trade-off. That's cool you look at. The other biggest issue with the other big issue with minimax trees for games is how do I score the instinct? Like, how do I score a game of chess? Especially if you just go to look ahead, where you can't just go, oh, if the thing you're only looking ahead like 5 moves, so you can't just say, oh, well, this one gives me a win and this one gives me a loss. I've got that's why they tell us to do Kalaha. Kalaha is a very easy heuristic. It's your things in your pit minus the things in their pit. With something like chess, it's really hard to pick a heuristic. Tic-tac-toe is relatively easy. The traditional one is 100 points for 3 in a row, 10 points for 2 in a row, 1 point for 1 in a row, and that works because there's no possible state that will give you more than 100 points for that 3 in a row, so you won. But for something like chess, it's really, really... I mean, you can do it, because minimax trees in chess exists, but it's kind of difficult.
I think I've heard that the computers tend to play. They don't play for position, they play for pieces.
Yeah, but it's not the best position.
So they have complete trees reversals and they've made tables now for 8 pieces on the board and down.
Yeah.
But you start off with 32 pieces on the board.
Like, again, so I mean, but you're not just solving it, right? You gotta actually try it with a heuristic, and that's really hard to come up with. But for something like, but the thing about heuristics is that if you want a computer to weight itself to particular moves, well, it's quite easy. You just pick the appropriate heuristic. So let's say we're gaming nuclear war, and I want my computer to understand that the best first strike is no first strike at all. Because the only winning move is not to play. I want to teach it utility. I want to teach it not to launch nuclear strikes if it's not being attacked, which is a pretty important, thing you want in your first response computer. You don't want it to be launching nuclear missiles, of its own accord. Well, I mean, let's assume that there's actually something to gain with a nuclear first strike, because really what you're doing is launch nukes at other guy. Everything else is really just messing around with detail. More or less, think about it. But let's assume that there's something to gain here. I'm assuming there's gaining flight trajectories or something. Or like optimal launch spots. Well, there's a fairly easy way to make it so that it will never nuke anything. It will never act of its own accord. It's got a whole bunch of options, right? Launch 0 nukes, or launch, I don't know, whatever the fuck is launching here. It's a magical supercomputer. It has 9 infinite computational power. It's magical. Okay, well, it can launch 0 nukes, or it can launch all of these. Now, what's going to happen if I launch nukes? Well, the enemy is going to launch nukes. So what if I want an accurate heuristic? If I want a heuristic that will ensure that it will never launch a nuclear strike on its own first move, well, here's my heuristic. Here's what my score should be. My casualties minus my casualties times 0.999, whatever number you want, close to 1, plus their casualties times 0.01. Right, so this means that this value will always be way less than this value. So in any event where I'm launching a first strike, my options are to launch no missiles at all and not launch the first strike. This will give me a value of like 0. Any of these will give me values of, minus 1 billion. Because any casualties that I inflict on them will be magnified, will be, minimal compared to the amount of casualties that I lose in this heuristic, the weight. So in the event of a first strike, the best option for me is for this computer is never to launch any missiles at all. Because in this game, the minimax result, the maximization of the minimal gain, the minimization of the maximal loss, is to not launch any nuclear missiles at all. However, if the Soviets strike, well, that's a completely different story, right? Then, well, I've had my options taken away from me, so my casualties are still going to be massively negative, but I can compare these maximally negative casualties against other massively negative casualties and work out which one gives me a better option, right? Because, hey, even 0.01 times 1 million is greater than 0.01 times 999,999, right? So, like, I've got a computer that can respond to a first strike, and I have a computer that will launch a first strike in a turn. Why the hell didn't they just do that? Rather than having to go through the steps that, okay, this is going to start a nuclear war. So that's why the scene doesn't make sense. Like, even assuming that it learns utility from playing tic-tac-toe against itself, well, you're just stuck at writing heuristics, right? Because this could have done the job easy. I mean, when they created this game, Server Nuclear War, it's clearly doing it with a minimax tree, because that'll give you the minimax. They'll give you the minimization of the maximum loss. But obviously gave it some kind of heuristic. They just gave it a wrong one, and now they're wondering why it's trying to launch a nuclear war. There's a really simple way to do this. I just came up with it in like half an hour last night.
Does that run into problems though if the computer is genuinely self-improving and therefore writing its own heuristics?
Well, I guess that like it's not like I doubt they like.
Yeah, because the computer is sentient, you can run into problems with the computer changing the heuristics it's used from ones that you consider sensible to ones it considers sensible.
So
It
why
has a
would
personality, Grisha.
But why would playing tic-tac-toe against itself change that heuristic?
Do you want Terminators?
I don't
This is
know.
how you get
Grisha, we
Isn't
don't
how you
know.
get
All we
Terminated
know is that it's sentient.
RFA in the sky to avoid
not fully.
What?
All we know really is that it's sentient and doesn't think the same way we do about nuclear war because it'll survive it.
So why would you build? This is the real moral of war games. Is if you build a computer to control your nuclear first strike system, make sure you know what it does first. You dumbass.
I thought it was life finds a way.
Life finds a way.
There is there's an aspect of negotiation theory which has to remove choices from themselves to strengthen your bargaining position. So people now have an automatic response,
Yeah.
which means that the human equation is taken over.
Yeah. Well, that's the advantage of it. I mean,
Yeah.
I was gonna get to this. I'm actually gonna get to this. The thing about okay, so automatic response systems to nuclear first strikes exist. The Soviets built one called Dead Hand. Basically, if they lost communication with Moscow, no matter how great your first strike is, the nuclear missiles, if they lose communication with Moscow, they launch, no matter what. This ran into problems around about 1983, where there was a little bit of a malfunction, and the radar started detecting oncoming nuclear strikes when something bugged out. I think that was an AI bug.
Oh, that wasn't the red alert thing?
There were several different glitches. One of which was that it saw clouds and thought they were nuclear launches.
That was it.
Formation ducks.
Yeah.
So I mean, occasionally these that ran into phone problems when occasionally these strike response systems would malfunction. But I mean, these things existed. They just weren't sentient, and they weren't exactly automatic. They launched according to pre-approved flight plans. And most of that's because there's really not a lot of variation between, how you launch nukes. At the end of the day, you pick a target and you point it at it. Because, as I will talk about later, you can't really defend against a nuclear attack in an MAD scenario. You can't, for a reason I'll get to later. So, let's talk about chickens. I'm probably going to be delving into IR here, but I'm not really an IR guy, so if I'm full of shit, feel free to tell me. This is why I'm glad that IR people like this. Okay, I'm approaching this from a very strictly game theory perspective. You got to remember that. So I'm probably going to be making blanket generalizations that don't really make sense for kids. Bear with me here. So nuclear war can be safely modeled from a game theory perspective as a game of chicken. You guys know what chicken is?
Yes. Yeah, it's delicious.
Just for that, I'm going to explain it. Okay.
Only in
Let's give a practical demonstration.
Alright.
With the person who doesn't know what it is.
I have run at each other. Right. Okay, basically the idea about chicken is that you two people drive at each other, and the first person to swerve away loses. So when you play a game of chicken, because you're an idiot, you have two choices. You can keep going, or you can swerve aside. So So there are four possible things. Both of you swerve, one of you swerves, or the other one swerves, because that's really two states. And you both crash, which is the absolute worst case for both of you, because you both die. Ideally, you'd want to avoid that, but at the same time, you want the points that you get for winning, because, I don't know, you're a massive gory hound. It's another game that makes no sense for people to play it, if people do. Or you both crash, which is the worst for you. So, you can grab them, actually enough. Wow. Okay. So this is what's called a game matrix, a payoff matrix. This is my personal way of displaying it. I've got the flashes, that's not really traditional. But anyway. Normally you meant to have like a pair. That doesn't really matter. I like flashes to actually make you. So you've got two sides. Let's say you've got a specific instance of a nuclear crisis. Of a crisis that threatens to go nuclear. Say you've just found the USSR putting nukes in Cuba. You're putting nukes in Turkey, and you just found the USSR putting nukes in Cuba. It can't possibly think, right? Well, I got famous or anything. So you have two choices. You are the USA. You have two choices. This should be blue. You can swerve, and you can keep going. Now, if you swerve and the USSR swerves, you both get 0 points. These points are arbitrary. They're important, but they're arbitrary for this example. You can swerve, and the Soviets will keep going, which means that they will have nukes in Cuba, and you won't have nukes in Turkey. They've got one up on you. That's bad for you. So you lose points, and they lose, and they gain points. Or you can loss them out of the room, and you can keep going, and you can keep your nukes in Turkey, and they will back down. And then they will lose points because now you have a really great first strike option against them, and they don't have that. Or you can keep going. The end result of this is you both launch your nukes at each other and kill each other.
And everyone else.
And everyone else. But, you didn't care about anybody else, right? So that's -100, -100.
That equals Australia wins.
Yeah.
Unless you're at any of our radar stations.
I think we lost 150 million one more game next time.
Moving on. So there's a pretty, for some games, you can approach them with what's called a pure strategy, which is you only pick one option and you always pick it. It's called a pure strategy. I'm not going to go through international equilibrium because they're hard. The math isn't hard, but like getting your head around them conceptually is. But you can approach this with a pure strategy. What you do is you pick every, say the United States, you pick a square. Is there any interest for you to deviate from the square? If I'm the USA and I pick, and I'm on this square, well, if the USSR is swerving, why would I swerve? I should keep going. So in this case, you're going to default to that. Same with the Soviet Union. In this stage, if I'm the USA, if the USSR keeps going and I swerve, well, now I get -100. -2 is looking pretty damn good. I'll stay there. If I'm the USSR and the USA is swerving, why the hell would I swerve? I'm going to go to that. I'm going to stay here. Same for this. I'm going to stay because it's the same thing with the values reversed. If the USSR, if we're both keeping going, and I'm the USA, I am the USA, and I'm keeping going, well, I'm going to lose, so I better swerve, so I move up here. If I'm the Soviet Union and I'm keeping going, and we're both keeping going, well, I better swerve. -200 is better than it's worse than -2, so I'm going to swerve here. So what this means is that from pure strategy in the actual equilibrium, there are two possible options. Either this one, which is one keeps going, which is US swerves and Soviet Union keeps going, or the USSR swerves and the USA keeps going. These are the two results if they're both using pure strategy in actual equilibrium. This is completely useless because I don't know who's keeping going and who isn't. I have no clue. Like, it doesn't tell me anything other than, well, one person will swerve and the other one keep going. This isn't a pure strategy. There is a pure strategy in actual equilibrium. People who actually know what game theory is, there is a pure strategy in actual equilibrium. This is it. It's just that it happens. The pure strategy in actual equilibrium solution is fucking useless. It doesn't tell you anything. So what you could approach what's called a mixed strategy, which is essentially I choose between these two based on a probability, based on like a metaphorical coin flip. And that's the other option. So you can work out what the optimal probabilities for this are. I'm not going to go through the math in front of you because it's boring. It's not boring. It's cool. It's just like to get your head around. That means I have to explain what math equilibrium is. So the optimal strategies are P swerve 49 on 50 and P keep going are 1 on 50. So if I'm the USA, 49 times out of 50 I'm going to swerve, but 1 time out of 50 I'm going to keep going. Same with the USSR. 49 times out of 50 I'm going to swerve, 1 time out of 50 I'm going to keep going. The problem with this is that 1 on 50 squared times, we're both going to nuke each other. That's kind of a big problem, but given that the only real way you can approach these is with a mixed strategy approach, it's kind of inevitable. So, but the most common option is that they both swerve. The most common odds of that are 49 on 50. Squared, never mind, I don't want to work it out. Can't remember off the top of my head.
Something big over 25.
Hold on, give me a second. 9 times 9 is 81. 4 times 9 is 36, that's 44. 9 times 4 is 36. 9 times 4 is 98. I don't have a calculator on me. I don't like using calculators with simple stuff like this because that means that everybody forgets how to do like long multiplication. That's pretty bad. So 2,401 times out of 2,500, they both swap. And that's kind of, if you take chicken and this example as a case, well, that should have been, supposedly that should have been a very reasonably high risk of some kind of nuclear war happening during the Cold War. These numbers are arbitrary. I did this because there was a YouTube tutorial that did the math for me and I didn't want to have to do it again myself. So I'd like recalculate it. They're actually really easy to calculate, just that if I recalculated it, I'd explain to you how I recalculate it. I think that the point score you get for both of you keeping going and nuking each other should be significantly lower than -100. Because the optimal probabilities that you're using are dependent on the payoff. Because they're a function of the payoff. But so I mean, really, if you want to approach this from anything vaguely resembling a realistic model, which is difficult because it's hard to push IR and real world concepts into game theory, you can do it, but you've got to simplify quite a bit. Well.
Don't tell IR here, isn't that?
Yeah.
I mean, look, game theory is a really powerful tool, but like, you kind of got to take into account exogenous circumstances. It's the economics problem. Everything works great, right, until you actually try to do it. So, I mean, if you want to approach this with anything vaguely resembling some kind of realism, the probability of two people actually nuking each other becomes vanishingly small.
Just wrap it up.
Can I just say that vanishingly small is still sort of high when we're talking about the elimination of life on Earth?
I was getting to that. I was going to say it's vanishingly small, but it's that.
However, this is why we agree that the Cold War was bad.
I mean, by some reason, if both people approach a pure strategy dash equilibrium, well, it's impossible, right? They're always going to do this. It's just that, why would anyone pick to always swerve? That game's not really Cold War. Yeah?
Would you think that chicken or prisoner's dilemma is more applicable?
Definitely chicken. If we both co-op, I'd probably go with keeping going because the payoff that you get for I'm trying to remember the graph for chicken. I figure that say prisoner's dilemma, the default state is that they both betray each other. So then you both nuke each other. That's kind of experimentally not an accurate model. The other thing is that here's why. Now I remember. With prisoner's dilemma, there's never an incentive not to keep going. Here there is. Yeah.
Is there enough time to say what prisoner's dilemma is?
Okay. Yes. I was going to talk about human missile crisis as an example of it, but it doesn't really matter. Yes, prisoner's dilemma. You can turn this off because it would probably be helpful for that gap in space.
Sure.
You can turn it on later if you really want. If you really want to hear me talk, computer scientists talk about the human missile crisis.
Well, that's why I'm here, of course.
I'm not talking about computer science. I'm only here for free food. Who are you? Why are you standing in front of my food? Okay, prisoner's dilemma. You got the two prisoners in two separate rooms. You're trying to get them to confess on each other. So your prisoners have, and they can't talk to each other. They can't communicate. Your prisoners have two choices. Number one, I can betray you.
You may want to cover it instead.
I may. Don't tell me what to do.
This is why I said you may.
I may.
It's actually a standard police technique as well.
Yeah. It's also a very good model for a whole bunch of stuff, like competitive pricing between firms.
Or student campaigning.
This is literally like the first model you will ever learn, actually. Prison, you can betray him, or you can not betray him. Simultaneously, prisoner 2 can betray you, or they can not betray you. If you both betray each other, you get like 20-year life sentences. Both of you. 20 to you, 20 to you. If you betray me, and I don't betray you, I get like 10 years, I think is the... No, you get worse. You get worse.
40 years?
Huh?
It's 40 for the one betrayed.
Yeah, that's right. That's the difference between it and nuclear war. Because this is worse than both nuking each other. So it's just... And I mean, not having nukes in Turkey...
Just fill out those,
yeah,
right?
but not having nukes in Turkey is significantly better than being nuked, right? Yeah. So it's just not a good description. So that's 40, and they get like 0 usually. Here it's 0. If I betray you and you don't betray me, that's 0 to 40. And if we both don't betray each other, it's like 5-5.
Yeah.
So we can get the best possible option for both of us by not betraying each other. Here's the thing. Let's say I have two choices. I'm this guy. I'm Tom. Let's say I have two choices: to betray you or not betray you. Well, let's think about it this way. If you betray me, what is better for me? Let's say that you betray me. Let's assume that you're going to betray me. What's better for me? Well, betraying you. That way I get 20. Let's say you don't betray me. What's better for me? Betraying you. That way I get 0. So top player is always going to betray. Let's say I'm the side player. If you betray me, what's better for me? Betraying you. If you don't betray me, what's better for me? Betraying you. So the end result here is that there's no reason for any player to do anything other than betray each other. So they both betray each other, and they both get the 20. They both get 20 years in prison.
That's why this is a standard police technique.
Yeah. So it's one of those really good models. So that's the prisoner's dilemma. The prisoner's dilemma is this: the Nash equilibrium is they both betray each other. It's a pure strategy for both of them. So yeah, it's distinct from chicken because betraying each other in chicken is far, far worse than one of you swerving. Yeah, that's the difference. Okay, that's pretty much the end of my talk. Is there any?
Do you want to go over the Cuban Missile Crisis? Because we've got a little bit of time. We've got a hair past a freckle on time.
Okay, I've got 3 hands to go. Feel free to turn the thing on.
But introduce it.
Okay, basically had a thing about the Cuban Missile Crisis, and it as an exemplifier of this most likely option of them both swerving. To give a bit of context, When did Castro take over Cuba? 60.
Castro took over in the late 50s, I think 59 or 58.
58, yeah.
And then the crisis is in
63.
62.
Okay, so the U.S. had a bunch of nuclear missiles in Turkey. The Soviets thought this was a massive threat because that essentially raised your response. Like, Turkey's here, USSR is here. That, and here, and here, and over here. So that essentially drops your response time to an enemy nuclear strike. Tiny. So in 58, I think, Fidel Castro and the communists took over Cuba. In the United States, here's Cuba. 62, the United States finds out that there's nuclear missiles in Cuba. Bring a picture.
Just like they were initially setting up the plan, setting it up at that point.
No, they had the missiles there.
Yeah.
So America didn't know that at the time, but they had missiles there.
So it turns out that if you put nuclear missiles in Cuba, your response time for a Soviet launch becomes zero. So the United States tried to blockade Cuba to stop nuclear missiles arriving, and they were threatening to sink Soviet ships. The Soviets essentially said, well, if you sink any of our ships, we will retaliate. And when two nuclear armed powers threaten to retaliate against each other, that means nukes. That means they're going to nuke each other. So it came very, very close. In fact, the United States actually did shoot at the Soviet submarine. The Soviet submarine decided to not respond to it. This happened. In the end, very, very close to a nuclear war, Kennedy rang up Khrushchev and said, okay, we'll take away the nuclear missiles from Turkey if you take away the nuclear missiles from Cuba. Khrushchev says, okay. They both swerve. Neither of them has nuclear missiles off the butt of the respective enemy. Okay. They've kind of gone to the truth state. And I know that's kind of a shaky hand because, people didn't know at the time, but by my reading, the Soviet Union kind of won that one if you look at a kind of longer term response. 59. No. 59, right? Let's look at the score here. 1959. U.S. score, Soviet score. U.S. has nuclear missiles in Turkey. That's 1 point. Soviet Union does not have nuclear missiles in Cuba. 0 points. 1962. U.S. has nuclear missiles. 62?
1962.
Yeah. 1962. U.S. missiles in Turkey. Soviet missiles in Cuba. 1964. No nuclear missiles in Turkey. No nuclear missiles in Cuba. Who has benefited from this situation? Yeah.
This is a somewhat delicate and contested issue about who wins, especially since the other factor here is prestige. America didn't tell anyone they were taking the nukes out of Turkey.
It was one of the major contributors to Khrushchev.
Yeah, I know.
Yeah.
But
Kennedy gained a lot of respect for disarming the situation. Khrushchev lost a lot of respect.
Even though Kennedy was probably the biggest antagonist in the situation.
Yeah, so Kennedy
It's
won.
complicated.
But did the U.S. win? Kennedy won and Khrushchev lost, but did the U.S. win?
America always
It's complicated.
I know. Well,
Except in Vietnam.
if you look at the specific...
Who was
North
the
Korea?
reason that they didn't went on to have nuclear starts off each other? Because
Well, absolutely nothing. How can you get rid of those? You need to ram two submarines against each other to precipitate a crisis.
That would be the best game of chicken of all time. Oh my
Those
god.
submarines are valuable.
Nuclear explosive chicken.
I
Call
think
that
That's
nuclear.
like the nuclear duck. If it looks like a duck, cracks like a duck, it's probably a nuclear weapon. I think
Anyway.
that was meant to be
Anyway.
right?
Anyway,
Any other questions?
Yeah.
so does that explain what your question was in terms of the prisoner's dilemma, Clara? Did that explain?
Yeah.
You do first year economics, I'll teach you that.
Okay. Well, thanks
Yay.
for
Thank you very much.